Okay, good afternoon all. Many thanks for attending this course HPC for CFD using Code Saturn. First going to give you an overview about what Stfc is. This is where we and I are coming from, and Juan will introduce EDF more in the next presentation. So basically, Stfc is a Science and Technology Facilities Council. It's part of UKRI, where there are 7 councils. And there are several facilities and several locations. And so he operates in 7 separate sites, some of them in the UK and some of them abroad, as you can see in La Palma or even Hawaii for telescopes. So Wei and I come from Daresbury Laboratory, which is between Liverpool and Manchester for people who are abroad. And we come from the computational engineering group over there. So the main feature of the course here are all related to Code Saturn, which is a CFD software, and which is open source. So basically, for the first tutorial and some other tutorial today and tomorrow, we are going to use a virtual machine and look at how to set up a simulation for a laminar flow. Then the second tutorial is going to be about preparing a large eddy simulation coupled with conjugated transfer. And this simulation, the plan for this simulation is to run it overnight and post-process the results tomorrow morning. Then we're going to look at some of the features of Code Saturn to try, or at least to assess the performance using some of the tools available, and also look at in situ tools. So the tutors are Juan Uribe, who works for EDF, Energy UK, Wei Wang, and myself, who work at STFC at Daresbury Laboratory. So here the agenda. So after this presentation, we're going to give you another presentation to explain how to upload an SSH key for you to access Archer 2 from the virtual machine. So first, you should have received how to get this virtual machine, and the transfers of files will be from the virtual machine to Archer 2 and not from your own machine to Archer 2. So then we will look at this first tutorial where we're going to explain how the graphical user interface works, and we will run that simulation on the virtual machine. After the coffee break, Juan is going to introduce how to use user subroutines in Code Saturn. And then you'll set up another tutorial for large eddy simulation and heat transfer with, again, application to tube bundles. And so the settings are going to be on the virtual machine. Then files are going to be transferred on Archer 2, and the simulation going to be run on Archer 2. And tomorrow morning, you recover the post-processing files, which are going to be generated during the night, and you copy them back on the virtual machine, and then the post-processing is going to be carried out there. So later on, we give a presentation about high-performance computing, mainly related to Code Saturn, and we give a smaller introduction to Archer 2 as well. This is going to be followed by some optimization tools, and also we will look at the influence of the partitioning and some hybrid parallelization, and that has an influence on the time to solution. And after the coffee break, we'll look at some in situ tools available in CodeSaturn. And we will finish tomorrow around lunchtime. We are going to look at the second presentation. So Juan, if you could load the second presentation. I'll stop sharing this one. So if you could load the second one for me, please.
Yes.
So I've got a question for you. Did you all? I mean, did you get the virtual machine? Do you have it already working? Hello?
If you have problems with the microphone or the camera, you can use the chat on the bottom right of the page. I sent an email yesterday with some links to the files that we're going to be using. Could you please let me know if you got them? Okay, one person got it. Oh, brilliant. So there's two ways that you can do the exercises here. You can either have your own installation of CodeSaturn in your own machine, or you can use the virtual machine that we sent. So if you have your own installation, you should have been able to log in using the instructions that were sent when to create an account on Archer. If you downloaded the virtual machine, then you will need to do the same thing, but from the virtual machine. So the virtual machine will have a specific address that you will need to register in the safe. So can you show me, is there anybody using the virtual machine, or are you all using your own installation of that? I can see that Megan said that she's got the virtual machine, but I need to know if there anybody else using the virtual machine. Okay. So this chat, should we just show them just in case?
Yes, I'm going to do that. In the chat, I'm going to make a. Okay, for the people who are going to try locally, we have to send you the PDF files then.
The PDF files should be in the link that I sent yesterday. They're shared on OneDrive.
Okay. Okay, thank you. Okay, so we need to. Okay, so basically, if you have the virtual machine, you should reach that point. So when you load it, you see, and you see that in the folder .ssh there are several files, and the one to upload to the to Archer 2 is id_rsa.pub. And so, as Juan said, for people who are not using the virtual machine but their own account, this might not be useful because they probably can access already Archer 2. So this is mainly for people having the virtual machine, but I don't think it harms to have several SSH keys anyway, and safe. So if you just give me a second. I'm going to add to this SSH key. So basically, the file id_rsc.pub. I'm going to add it to the chat now. Yeah. Thanks, William. Yeah, that's what I tried to say. Thanks, William. So basically, this is the SSH key you will have to upload. So the way to do that is to log on Safe. So you probably have done that already before, and then you go to the corresponding account, login account you've got. So I've got several of them, but you might have only one. And then from there, when you're on that account, you need to go to add credential, and from there you click on next, and then you add the SSH public key, not as a file, but in the box that try to highlight, and use and click on add. And then from there, that's what it should show. You see, the identifier should show code Saturn at code Saturn. Yeah. So basically, when you get that, you're ready to go from the virtual machine. I mean, to log on from the virtual machine. Yeah. So at this stage, so that's what I try to do. So that's my username. VCZ something. So, and he returns the password. So it finds me basically. And if everything goes fine, you reach Archer 2 with a welcome to Archer 2. Yeah. So could you let us know how it goes? If you want, I can send you this presentation by email.
That presentation is on the shared file as well. Shared folder. For your reference, if you open the web browser in the virtual machine, the safe login and the page for the course are bookmarked, the same as with the shared file, shared folder. You should have the link there to the rest. I'm gonna copy the link again for the share folder in the chat. Yeah, thanks.
Sorry. Okay, so can you let us know how far you are for people who haven't told us already? I just sent the presentation to. Okay, so that. Debasish, you seems to have some problem with the virtual machine. Could you explain us which kind?
I think it's showing some kind of problem like USB 2 is
Oh,
not
yes.
found, something like that.
Okay, so when you start it, go to the settings,
Okay.
and you can unclick the USB key, and click the USB key, box. Or yeah, so either before you start and just when you start it, and then start it again, and it should work.
Okay. Okay. Thank you. Okay.
Thank you.
I can show you if you want. Before you start your machine, if you go to settings, you see that there's a USB setting. You can disable the USB controller. USB, disable that. So you have a different side. Okay, I see more people are looking.
If any of you have got some issues, could you let us know, please?
Yeah, I managed to get a virtual machine, but what I really got is just a black screen. A black screen of the virtual machine.
Are you using Windows, Linux? Which version of VirtualBox are you using?
I use Linux.
And which version of the VirtualBox are you using?
Let me check. I think it's a 5.2.
Okay, it should be at least 6.0.
6.0. All right, so I have to find a new version. Okay.
Any other problems? Right, so we'll let you go. And we'll start with the introductions and we'll check again before we start doing the exercises anyway. If you have any problems, please post it on the chat or let us know. Okay.
Juan, can you just load the same presentation, please? There's a file about which quickly introduce Archer 2 at the very end. No, is the other one is a safe one. Sorry. Okay, it's okay. I'll go. Okay, so this is a very quick introduction to Archer 2, and so this is a machine which is much more complex than so this is a machine which is much more complex than UPC, for instance, because there are several disks that you use depending on what you want to do. Basically, you've got first some logging nodes. So the logging nodes allows you to access at least two folders. One, your home, so that's where people usually install software, and the work directory, which can be another machine called Scratch directories, and that's what you run the simulation from. So usually in the home directory, you got not much disk space, and on the work directory, you get many more. So if you can see in that sketch, actually the work directory can access the compute nodes. So basically, from the work directory, you're going to submit a simulation through what is called a queuing system. And at the end of the simulation, the results are back on the work directory, onto the work directory. So this is a little bit tricky to get used to it, because hoping that everybody knows a little bit of Linux, I would recommend people to type pwd to check which directory they are in regularly. For instance, it's not possible to submit a simulation from the home directory directly. So the machine is the UK National Facility. So it's a HPE Cray machine, so which has about 6,000 nodes. And so the nodes with standard memories are the regular compute nodes, and they also nodes for high memory that can be used for pre and post processing, for instance. So the processors are such that you've got two 64 cores processors. Cores per node, so which makes it in total 128 cores per node. So basically, any simulation will be on 416 cores or MPI tasks. It shouldn't run on this machine, for instance, except if you require a lot of memory. But for code saturn should not be run, for instance, with 16 MPI tasks on that machine. So the memory per node is quite high, with 256 gigabytes for standard memory and 512 for high memory. But the memory per core is quite small, with 2 gigabytes. for standard memory and 4 GB for high memory. And you need a connection between nodes. Of course, you've got connection as well within the nodes, but the connection between nodes is actually the when you run a large simulation, the one which is the most important one, and is based on a slingshot, which is 2 times 100 gigabit per second, and which is a bidirectional per node. So this is just a very short introduction. There's much more information under the hardware pages of Archer 2. So feel free to have a look, and please let us know if you've got any questions. Okay, thank you.
Okay. Any questions? Feel free to unmute yourself and ask. Juan? Okay, so we'll continue. I'm gonna now move on to the next presentation, which is talking about Code Saturn, with a brief introduction to EF. Well, as Charles says, my name is Juan Uribe. I work for the EDF R&D UK Center, and I'm going to be talking about first a brief introduction of who we are, different landscape here in the UK, and then we'll go through the actual code, and the basics of how to run a code case, and how to do processing. It's very basic introduction. Then we'll go into a first tutorial that will be very simple. You can do it on any desktop machine or in your virtual machine, and then we'll go very quickly to something more complicated, and hopefully that by the end of the day you can launch simulation that will run overnight. So EDF in the UK owns 14 gas reactors and 1 water reactor. We're currently the only nuclear operator in the UK. We're building 2 new reactors in Hinkley Point C. And out of those 14 reactors, there's been 2 sites that have been recently shut down and are in the process of being defueled, and later on they will be commissioned. So we are part of the EDF group, which is partly owned by the French state. We are a small part compared to the rest of the group, but we're one of the biggest parts that are outside France. The research and development it's made up of 12 international centers. We have a lot of PhD students in different parts of the country, and we have a lot of researchers as well that look into all aspects of electricity production, from the generation to the distribution to things like smart meters, etc. We're based in the UK in 3 different sites at the moment. Manchester is one of them, where we have the Modeling and Simulation Center together with the University of Manchester. So we're about 60 people in the UK, with many different nationalities in working at very different type of research and development. Some of the activities that we look at is modeling and simulation, as I mentioned, for nuclear power plants, but also for offshore wind and environmental hazards. And these include things like climate change and solar storms and things like that, for example. We have people looking at what we call smart customers, which is basically everything that's downstream of the next generation. So how to make buildings and houses more affordable for energy point of view, how to help with the things like smart meters or helping communities to use better electricity. We also have a group with digital innovation, so they do all the fancy things like blockchain and virtual reality and all that. And we have people looking at open innovation and being aware of what's happening in different parts of the country and what can the company gain from different startups. So we work in collaboration with many companies, government departments, and universities. Here are just some of them. One of them is the Science and Technology Facility Council, that Charles mentioned before. So that's pretty much EDF in a very short glance. And now we're going to talk about what is over here, which is the Code Saturn. Code Saturn is a three-dimensional unstructured finite volume code. It was made open source in 2007 on the basis that we are an electricity company, we're not a software company, so we don't really want to make any money from software. We just have to make sure that we can ensure the quality of the software for the nuclear applications that we use it. Therefore, that's why we decided to go and make it open source. Code Saturn, in its open source version, is a single phase solver. There's a multi-phase solver, but that is not open source. That has been developed with other partners in France. It's called Neptune CFD. But the one that we're going to be using is single phase code. That has various turbulence models. And it has a lot of different modules for specific physics. So some of these specific physics are very much geared towards the nuclear industry, but there are some other things that are more general, like compressible module ALE, for example. The code is written in C and Fortran, and all the graphical interface and the file manipulation is on Python. There's a graphical interface which is available in Qt, and you will be using it throughout the course. Code is parallel. It uses MPI and OpenMP, and it's very good. Has a very good scalability in machines like Archer2. You will see later. One of the key aspects of this code is that it has gone through a very thorough validation verification process with each release, which has about 300 cases and growing. It's a semi-automatic validation process, and it's done for every major release, which is every 2 years. This is to comply with the nuclear regulations when we use the code. It is a very portable code. You can work on Linux in or variations of Unix as well as Mac. Saying that, I don't think we have tested it in the newest Mac with the ARM processors. That'd be something be interesting to know. The code is split into different parts, as you can see here. There's a graphical interface that is a very simple standalone module where you define all the options that you want for your simulation. The file names for the meshes, and you put your boundary conditions and your numerical setup. Then that setup file is read by the kernel, which reads the mesh and do any modification that is necessary for the mesh. If you want to modify it, there's some tools that we'll see tomorrow that can help you when you want to modify a mesh. And it creates all the geometrical characteristics that the code needs from mesh. So things like face centers, cell centers, normal vectors, etc. Once that pre-processing stage is done, the solution starts with the Navier solver, basically, and any other specific physics modules that have been defined before. And finally, the post-processing files are written once the calculation is finished, or as the calculation is running, depending on what the user sets. And then those files can be read by other software. So important thing here is to notice that there's no mesh generator in CodeSaturn, although we're going to use a very, very simple Cartesian mesh generator. It's not intended to have a mesh generator. And it doesn't have a post-processing tool either. This is all done via other software. One way that we have combined all of this is through the Salome platform, which is also developed by EDF, in which you have CAD part, meshing module, and a post-processing module based on ParaView. We're not going to use that for this course. We're going to give you the meshes that you require, and the idea is that you learn how to solve a problem using CodeSaturn in a large machine like Archer2. And we'll be using ParaView for post-processing. So the graphical interface, it looks something like this. You'll have two different panes, one on the left, which is just a list of pages where you have all the different possible inputs that you require. And the idea is that you'll go from top to bottom, selecting what is necessary for the simulation. Some pages will appear automatically once you do a specific selection. So, for example, if you select that there is a solid zone, then the options for the solid will appear automatically. So the idea is that you go through all of these pages, and at the end you will have an XML file that will be read by the kernel when it starts the simulation. There's also a thing called the mathematical expression interpreter, so some things that can be set up as formulas. For example, you can put density as a function of temperature, for example, or you can put varying boundary condition. So it's a very simplified mathematical expression interpreter. And that's why you have the option to use what's called user subroutines, which are much more powerful and basically allows you to program pretty much anything that you want to do, if you know a little bit of C or Fortran. The graphical interface is actually not necessary to run a case. You can also set everything using the subroutines and some scripts. So that way, that means that the subroutines will always have presence to anything that you define on the XML file. So you'll see during the tutorial that you use a command which is code Saturn. If you're using the virtual machine, this has already been set up for you. If not, you will find it under the installation of your code, the bin directory. That command is a multi-purpose command. It has different topics or subcommands, and each one of those has different options. So when you type code Saturn, you will just see the help by default, and then you can select any other subcommand and type -h to see the different options. So for example, if you type code Saturn info --help, it will give you the help of how to get information about the code. You will have the different options to define which type of guide you want, the installation guide, the theory guide, or the user guide, for example. Or you can see the version number, or you can select which PDF reader you want to use to open one of these documents. These guides can also be accessed in the help menu of the graphical interface if they had been installed correctly. One source of information is the website. It is there's a lot of information there. There's a forum as well. There's a copy of all the documentation. There's the Oxygen documentation as well. That we'll go through that later. And there's some tutorials and examples as well. You will find also links to the YouTube channel where there's some video tutorials as well. So, as I said before, there's no mesh generator in code Saturn, but it can read a very large variety of formats, which most of the commercial mesh generators export in one way or another. So here are some of the most popular formats that you can get from one of these software. As I said before, the preprocessor works independently from the kernel, so you can check your mesh and visualize your mesh before actually having to run a case. You can check that the mesh is valid, but you can also see the quality index of the mesh, see the boundaries or any other zone that is inside the mesh, information that is in there. And after reading that mesh and creating all of this information is stored in files that you can post-process using Parably. So how to run a case? Before running a case, what you need to do is create a specific directory structure for the code. The code will run and we'd expect to have this structure and to have the files in the different folders. So this structure is based on what's called a study. So a study would be, for example, what we're going to do after, which is a flow over a tube bundle, right? And then you can have different cases, which each case would vary depending on, for example, you use different meshes or you use different models or different inlet conditions. So you can create a study with -s and the study name, or you can just create cases one by one after inside your study with the -c. If you use the option --copyref, as you will see in the tutorials later, it will also copy the two directories that have examples and reference subroutines. So you can also do that by the graphical interface. There's a basic text editor that allows you to do some manipulations of the subroutines. But if you want to keep a copy, hard copy of your directory, use this option. As I said before, with any command that you put in CodeCenter, if you type -h, you will get help. So this is an example of a case and a study hierarchy in your file system. When you create a study, you will see that you have a folder for each case, a mesh folder, and a post folder. Your case folder would be where you would put all the information for that particular case, and where everything will be stored after the simulation is completed. Inside your case directory, you have a data folder where you have a copy of the CodeCenter script, and where you save your XML file from your settings. You have the results file, which is where the code stores the results after it has run, and you have a SRC directory that contains any subroutine that you want to use and create. If you use minus copy ref, these directories will appear there. If you don't, then they're not copied. So in order to start the graphical interface, you go into the data directory, and then you type this CodeCenter GUI. That would bring up the graphical interface. You can create a new file by clicking on the white page button, or by going to File, Create New. And then it will go through all the necessary pages that you have. And as I said before, as you go changing these pages, some can appear, some or disappear, depending on the selections that you make. Once you've gone through all your settings and checked that everything is correct, you save the file, and you can click on the button that says Run, and that will bring another window, and that will allow you to select the number of processes that you want, the thread processes, and then the button that says Run Calculation. Once you do that, code has a different window popping up that's going to tell you what's happening. It's going to give you the different stages that the code goes through. So first it compiles if there's any subroutines, then it does the pre-processing of the calculation, copies all the data, does the pre-processing of the mesh, and then starts the proper calculation. And if everything goes right, you end up with the post-calculation operations, such as copying files and results files. As I said before, sometimes you need to use the Fortran or the C file in the user subroutine. So that's something to take into account. While the calculation is running, you can always use this convergence tool that will show you the residuals, the main calculation. In this case, you can see that you have velocity and pressure residuals, and you have also any probes. If you define them in your domain, you can plot the evolution of the variables in time. So this is very useful when doing unsteady calculations, for example. And if you want to use some specific physics, or you want to change something, you can always use subroutines. There's two types: there's the Fortran and the C subroutines that you're going to be using. And the best way to do it is copy any reference or an example that you want into the SRC directory. Everything that is inside SRC will be compiled, so you can create your own and use it any way that you want. But everything will be compiled. Everything that is C and Fortran will be compiled. If you want to run it without the graphical interface, at least you need to fill in the CS user parameters and the CS user boundary condition subroutine. We'll see that more about subroutines in another presentation later. And as I said, just remember that if you set some values in the Fortran subroutines, they will have precedence over whatever you set on the graphical interface. Another thing that is very useful is a script that you can use if you're not using the graphical interface, in which you can change the location or point to the specific files that are needed during the calculation. So things like where to find the restart file, or which run to use to restart from, or where to find the mesh files or something different. You can set it up manually there without actually having to open the graphical interface. Once you run the simulation, you will see this in the screen, which is the same thing that you will have on the new window that appears when you use the graphical interface. And in both cases, you'll see that it tells you where the results are going to be. So by default, Saturn writes a folder with the date of the run inside the results directory. Okay, so every time that you run something, it creates a new folder and it saves all the files there. So you never overwrite a previous simulation. But that also means that you're going to have a lot of files eventually. So you need to be aware that if you're doing very large simulations, that can grow to a very big size very quickly, and your administrator might not be very happy for you to have such a big share of the space. On the result files, in each one of these runs, you're going to have a listing file, which is a text file that has all the details of what happens through the simulation, and it's written as you go along. So for each iteration, you can have a series of information. And there's also some other files when you finish the simulation. You'll find things like a summary file that has the main settings that you use for your environment. So things like your environmental variables and machine that you use, etc. You also have a setup.log file that tells you more about the actual settings that we use after reading your XML file. And if the calculation finishes without any problems, you will have a post-processing directory, a checkpoint directory, and a monitoring directory. The checkpoint is a file that contains all the information that is necessary for CodeSaturn to restart the same calculation from that point. So it has information about all the variables at all the cells, things like max fluxes and previous values if you're doing second order time, for example. Things like that. What to do if you have problems? Well, depending on the stage that you have the problem, you have different files. So the first thing that the code will try to do is try to compile images and everything. If there's a problem with that, you can check the compile.log, okay, and that will tell you why is there an error. If it fails in the pre-processing stage, then the preprocessor, the log file, is the one to look at. Similarly, if the calculation doesn't go according to plan, it will tell you to check the listing or run solver.log file. And then you will have some information about what's happening. After the calculation is finished, you can look at the results. As I said before, it will create a directory with the date. So year, month, day, time. And you will have the post-processing directory with the files that can be opened by Paraview. These files have a copy of the mesh in its own format, so it would be a large file if the mesh is large, and there are single files per variable. If you chose to have monitoring points and to see the evolution of the variables as the calculation iterates, you will find that in the monitoring directory. Checkpoint will have a copy of the mesh file, a copy of what we call the main and the auxiliary file. So the main file will have all the necessary files to restart, and the auxiliary file will have information that would be used, but that is not necessary. So things like values of previous time steps or math fluxes, things like will ensure that the calculation is continuous in whatever order in time you were using. If that file is not available, you would just set those values to the default value, but it will run as long as you have the main file. It also has a copy of all the Fortran and C files that you used, and any user output file. So if you write a program that wants to extract a profile, for example, it will be in this directory as well. So effectively, after the calculation is finished, you will have anything that you need to rerun exactly the same calculation in there. So it makes it easier to compare when you do different runs with different parameters, you can always find out what was the difference if you forget data. As I said before, you have a summary and a setup log file, which is where most of the differences will be in between runs, as well as the XML file. The results file, as I was saying before, will have different files that can be used in Paraview. So those files are have the extension .case. That's what you load in Paraview. It's a simple, very simple text file that just tells the post-processing software what variables are to be read, how many time steps, and what's the mesh file. So the post-processing file is the one that is going to read the geometric file, and then the variables that you want, depending on your setup. You can change this frequency of how often the variables are written, so every n number of seconds or every n number of iterations, so that you can see the evolution in Paraview as well. By default, you have two different cases in Saturn, one for the fluid cells and one for the boundary phases. But you can create anything you want. You can extract a selection. Imagine, for example, that you have a very, very big mesh, and you don't want to have to visualize everything. You just want to see a subset of that mesh, or you can make it a function of any variable. So for example, you can just extract cells which have a temperature larger than a specific value, so that you don't have to copy very big large files and post-process them. So this is an example of how Paraview looks like for those who haven't used it. You basically load your files, and then you can do things like contours, you can display the mesh, you can display streamlines, vectors, and many other things you can do with Paraview. Your history files or your monitoring files set up also per variable. You can select which variables you want to monitor, and you select how many points you want to monitor as well. So each file will have the values of that variable and at each iteration or each time step. You can select how frequently they're written, and these are just text files that can be opened with any software that upload to the program. So for example, we use XMPrace or NuPlot, or you can even load it just directly on Excel, for example. And you can select which ones from the graphical interface or from a subroutine. And this is the sort of plot that you will find similar to what the track convergence shows you. Okay, so that's your very quick introduction. Are there any questions? No questions? You can raise your hand, unmute yourself, put something in the chat. Share your camera if you want. We're happy to see you, hear you, anything. Good, excellent. Okay, so I think we move on. We're gonna do now the first tutorial, which is laminar flow over tube bundles. And put it up here on the screen. So, as everybody is anyone that doesn't have a copy of this PDF? Okay. So now this has been written for you to go through the different pages and follow the instructions. And I'm not going to show you step by step how to do it. The idea is that you do it by yourselves. But we're going to be here for any questions that you need, any problems that you have. We do it this way because it's easier to answer the questions between the three of us individually, rather than having everybody having to wait for the other people to finish or to solve their problems. So let's see if I can make this again. What we're going to be doing is solving this type of flow, in which we assume a tube bundle. So this dotted line shows you what the computational domain is going to be. It's a 2D flow in this case, and we're just going to do a very simple laminar flow with a prescribed pressure drop. So we are setting the force directly into the code and allowing the flow to move. Okay, so In this case, you're going to be using 3 different types of meshes that we have provided you with the shared files. If you got a PDF, you should have got the files as well, but if you didn't, just please let us know. And the idea is that you go through the pages. It's going to tell you exactly how to run the code step by step. It's going to show you the same thing that I was telling you about, this file structure. So it shows you how to create that and how to navigate through that, and then how to start your graphical interface, and it shows you how to fill in the different pages that we need to do in order to run the case. Once you fill all of that, the simulation will be ready to run. So you run the simulation. It's a very small case, so you can run it locally in your computer in the virtual machine. And then you can check the post-processing files, familiarize yourself with the results, how to see the results, how to visualize things using ParaView, how to plot different profiles, and then compare with different meshes and different solutions. There's an appendix. If you finish early and you want to do something extra, you can try to add heat transfer to the simulation. Okay, it's not very complicated, but see how it goes, and if you want to do it, print. After that, we'll have a coffee break around 5:15, and the idea is to do the same type of flow. Instead of laminar flow, we could do turbulent flow much later using a large simulation, and that would be a much bigger simulation. It would be a 3D, and you will run that overnight. Before the end of the day, the idea is that everybody submits the job into Archer 2, and we come tomorrow and check the results.